Okay, good afternoon. In today's session, I will be discussing about some numerical examples on stresses in bars of uniformly tapering sections. You know what are the bars with uniform tapering? So the cross section changes uniformly. The cross section changes linearly from one end to the other end. That is uniformly tapering section. The cross section may be either a circular or rectangular. Okay. Now, in the first example, it is seen that the trapezoidal form, tapering bar with a trapezoidal shape. That means the cross section is rectangular. At one end, the dimensions being B and T. T is the thickness, B is the width or depth, you can say. At the other end, thickness is T, same, but the depth or width is capital B. So, the width changes from small b to capital B in a length of L. In a length of L. Okay. So, let us see what is the problem given. A flat steel plate of trapezoidal form of uniform thickness. Derive an expression for the total total extension. It should be the total extension for the thickness of 20 mm, which tapers uniformly from a width of 100 mm at one end to 200 mm at the other end in a length of 800 mm. If the axial tensile force is 60 kilonewtons, 100 kilonewtons at each end, find the elongation of the plate. Find the elongation of the plate. Okay. So here the width at left end is small b, which is 100 mm, and width at right end is capital B, which is 200 mm, and the length of bar is 800 mm. Thickness is uniform and is equal to 20 mm. Thickness throughout is 20 mm. Okay, and Young's modulus is given as Young's modulus is 2.05 into 10 power 5 Newton per mm square. Newton per mm square. Okay, so this is the data given in the problem. So how to find the total elongation? Okay, if it is a bar of uniform size, uniform cross section, then we can easily find if breadth is B and thickness is T, then we can find the extension, the cross sectional area being B into T. Okay, so the extension is delta L is PL by AE. Okay, this is for uniform section, bar with uniform section. We can easily get the total elongation as PL by AE. Okay, that is stress by Young's modulus into length. Stress by Young's modulus is strain multiplied by length gives change in length. Okay. P by A is stress, sigma by Young's modulus, that is strain multiplied by length gives the change in length, okay, of the bar. But for tapering sections, one dimension here is constant thickness, but the other dimension, breadth or width or depth, whatever you can say, okay, the other dimension is changing uniformly from small b to capital B here. Okay. So for this section, we cannot apply this formula. Okay. For that, what we need to do, you consider small element of length dx. Okay. Small element of length dx at a distance x from left support. At a distance x from left support. Okay. As the length is width is changing from small b to capital B in a length of L, what will be the change in width in a length of x? So we have to find the width of the section at distance x. Okay? Understand? So width of the section at distance x. By interpolation, we can obtain this. Okay? So how will you get this? The change in width in a length of L is capital B minus small b. In a length of x, it is multiplied by x. Okay. Now, the total width is b plus change in width. Okay. It is clear. So, b plus capital B minus small b by L into x. You can denominate this as capital B, small b and capital B, or b1, b2, it doesn't matter. We can use any notation, okay, as you wish. So, first we will find out the elongation of this elementary strip of width dx, okay, treating it as a rectangular element, treating this as a rectangular bar of length dx. With rectangular bar means with uniform section. Okay. So what will be the area of this area of section, area of cross section here? Width is b and thickness is t. So bx into t will be the area at distance x. Area of the section at distance x. Okay. So considering this small element, so here we are treating it as b1, b2 here. Okay, b1 is width at left support, left end, and b2 is width at right end. Okay, so width at section x, bx, is b1 plus b2 minus b1 divided by L into x. Okay, yeah. Bx is b1 plus b2 minus b1. This is the change in length per change in width per unit length. Okay, change in width per unit length multiplied by x gives change in length for a length of x. That is added to b1 to get bx. Okay, so here b1 is equal to, now bx is equal to b1 plus, this is replaced by k, some constant. Okay, b1 plus kx, where k is b2 minus b1 by L. Okay, so this is the width. So what will be the area now? Area of cross section at distance x, Yeah, this is width bx multiplied by thickness. So b1 plus kx multiplied by thickness, that gives the area. Okay, so knowing the cross sectional area, and we know that the element is subjected to an axial pull of p, axial pull of p. So under the action of load p, the extension of this elementary strip is given by, extension of this elementary strip is given as p l by ae. The expression is pl by ae. Okay, here load is p, same load will be acting throughout, and length of element dx by area ax into E, Young's modulus. Okay, PL by AE. So this expression we will use here. Okay, so if you observe this, it depends on x. It depends on x. Okay, so total elongation is obtained by integrating this between the limits 0 to L. That means from one end to the other end. From x is equal to 0 to x is equal to L. So by integrating between these limits, you will get the total elongation of the bar. By summing up the extensions of number of such elementary strips. Okay, this is the meaning. This gives the meaning that the total elongation is equal to the summation of the extensions of number of such elementary strips. Elementary strips. Okay, so we have seen the extension of one such element is this. So you will get the summation, total elongation, by summing up this. In other words, by integrating this. Okay, by integrating this. So the total extension is integral of this. Okay, yeah, delta L is equal to P dx by this one, this and this expression. Okay, P dx by b1 plus kx, k is some constant, okay, which is equal to b1 minus b2 by L, okay, into t, that gives the area into E, Young's modulus. Okay, so here taking the constants out here. Okay, what are these constants here? P, T and E are constants. Okay, so now the integral of 1 by b1 plus kx, integral of 1 by b1 plus kx, it is in the form integral of 1 by x dx. Okay, which is equal to log x into, in place of x we have b1 plus kx, so derivative of this, which is k. 1 by, yeah, we are replacing here b1, yeah, by replacing b1 plus kx as t, we will have k dx is equal to dt. So dx is equal to dt by k. So you will have log x by k, log x by k, replacing dx by dt by k, 1 by t dt is log t. Okay, log t. Understand? This one by k, here being constant, it is taken out between the limits 0 to L. between the limits 0 to L. So substituting the limits here, delta L, the total extension is P by TEK into log B1 plus KL, substituting L by B1 minus, actually we'll have to substitute 0 also. What happens when you substitute 0? It becomes log B1, this term is 0, divided by B1, that is log 1, which is 0. Okay, so this term is 0. So you will have log B1 plus KL by B1. And what is B1 plus KL? Nothing but B2. B1 plus KL is nothing but B2. So the total extension is given as PL by TEK log B2 by B1. So this is the expression for total elongation of trapezoidal bar of uniformly tapering section. Okay, bar with uniformly tapering section, the cross section being a rectangle. Understand? So this is the total extension for the given bar. So now for the given problem, the data is given like this, isn't it? So substitute these values. This is general expression now. This is general expression for any width B1, B2 and L, T. Okay, for any given values of this, you can get. This is general expression for total extension. Okay, now we substitute the given values here. So PL by TE into K. K is B1 minus B2 by L. B1 minus B2 by L. So substituting these values, actually P by TEK here, P by TEK, okay, no L here. So what happens in this B1 plus B2 by L, taking this L to the numerator, PL by TE into B2 minus B1. Understand? Yeah. Now, load is, you have to, while substituting, you should take care of the units here. P is given in kilonewtons, so first convert that into newtons. And L is in millimeters, T thickness in millimeters, Young's modulus in Newton per mm square, and B2 200, B1 100. Okay, all are in same units. Okay, you should have the units same. Okay, so this gives the total extension as 0.1352 millimeters. It is clear. So this is first example. Now second example here. Second example is something like this. Example 2 is about tapering circular rod. Tapering circular rod. Determine the reduction in length in a circular tapered steel bar with a cylindrical hole under a compressive force of 60 kilonewtons as shown in the figure. Take Young's modulus 2.1 into 10 power 5 Newton per mm square. So the bar is of circular section and tapering from one end to the other end uniformly. At one end it has 60 mm dia, at the other end it has 100 mm dia. Okay, and subjected to a compressive force of 60 kilonewtons. So here it has two portions, L, M, M, N. Okay, yeah. In this portion MN, there is a cylindrical hole of 40 mm diameter. Cylindrical hole of 40 mm diameter, centrally placed. Okay, is this clear? This is a hole, centrally bored hole. Okay, and the lengths of portions LM and MN are 100 mm each. 100 mm each. So how to find the total change in length? Actually here the change in length means the reduction in length because of compressive force. Okay, the length will be reduced. The length will be reduced. So to find the change in length of this tapering bar with a circular hole in one half of the length. So here we consider the portion LM separately and portion MN separate. So both are subjected to the same compression 60 kilonewtons. So the extension, the compression, okay, of LM we will find out, and compression of MN we will find out. Okay, understand? So first portion LM, let us consider the diameter at the left end. This is D2, say this is D1. D2 is 60, D1 is 100 mm, and D3, the diameter at section M is which is the midsection, actually 100 mm on either side, so it is the midsection. So at this point the diameter will be the average, 60 plus 100 by 2, that is 80 mm. That is diameter D3, say, at M. Okay, so the diameter at section M, this is diameter at L, diameter at M, average of 60 plus 100, that is 80 mm. So the extension of LM we can find out by using this expression, 4PL by pi E D1 D3, D1 D3, that is delta L1. Delta L1 is 4PL by pi E D1 D3. So what is load here? 60 kilonewtons. So convert it into newtons, and L is 100 mm. This is for only portion LM, so length is 100 mm by pi E, 2.1 into 10 power 5 Newton per mm square into D1 D3. D1 D3. So I have to take them in the same units, millimeters. Okay. Yeah, it gives the extension as 0.00758 millimeters. So this is the extension of portion LM, not extension actually, reduction, compression. This is not extension. This is reduction in length. because the force is compressive, there will be some decrease in the length. So reduction in the length of Lm delta L1 is 0.00758 millimeters. Okay. So now the extension, the reduction, change in length, say general word, change in length for portion Mn, the change in length of portion Mn which is also of length 100 and diameters are 80 and 100, diameter of hole is 40. Okay, diameter of hole is 40 and subjected to same 60 kilonewtons load. Okay, now what will be the decrease in length for this? Decrease in length for this. So how to find decrease in length? There is a central hole. There is a central hole in the portion Mn. So for this we consider again an elementary strip of thickness dx. Okay. So at a distance x from left end m. Okay. Now what will be this dx? What will be the diameter? This diameter, you call it, this is dx actually. Here you call this diameter of this as say d4, not d4, d dash, let us call it d dash. Okay. So what will be the diameter of this elementary strip at a distance x? That is obtained by interpolation. Okay, that is 80 plus, that is 80 means diameter at m, 100 minus 80, change in diameter in a length of 100, in a length of 100. And what will be the change in length in a length of x? Multiplied by x. Okay, so 80 plus change in diameter. So 20 by 100, that is 80 plus 0.2x. This is the diameter d dash. At a distance x, the diameter is 80 plus 0.2x. Okay. So what will be the cross-sectional area at this? Cross-sectional area at section distant x from left end. Yeah. Okay. Cross-sectional area at a distance x. What is the cross-sectional area? Pi by 4. Say, see, the diameter is d dash. There is a central hole of 40. Central hole of 40. So we want this area, hatched portion. Okay. Whose diameter is d dash. Pi by 4 d dash square minus 40 square. That is the cross-sectional area. Okay. So that is pi by 4. What is d dash? 80 plus 0.2x square minus 40 square. It comes out to be 80 plus 0.2x plus 40 a square minus b square, isn't it? 80 plus 0.2x minus 40. So pi by 4, 120 plus 0.2x, 80 minus 40, 40 plus 0.2x. Understand? So the cross-sectional area at a distance x is given by this equation. Okay. So now the stress sigma x, is at a distance x again. The stress on the element, is load P by area. So what is P? 60 kilonewtons. 60 into 1000 newtons by pi by 4. What is the area given here? Pi by 4, 120 plus 0.2x into 40 plus 0.2x, isn't it? Yeah. Pi by 4, 120 plus 0.2x into 40 plus 0.2x. Okay. So now the strain is stress multiplied by Young's modulus. Stress divided by Young's modulus. Sorry. Stress by strain is Young's modulus. So strain is stress by Young's modulus. Stress by Young's modulus. So what is stress here? 60,000 divided by pi by 4 into 120 plus 0.2x, 40 plus 0.2x into E. Okay. Now, you know what is strain? Change in length of element. That is, you call it delta x by original length. Change in length. What is the length of elementary strip? Dx. Okay. So change in length is Ex into length dx. Okay. So the total change in length is obtained by integrating this between the limits 0 to 100. Between the limits 0 to 100. So for that, first you substitute the values. Substitute the values here. Yeah. So delta x is equal to Ex into dx. That is sigma x by E into dx. What is sigma x by E? Sigma x by E is 60,000 by this. Okay. 60,000 by E. AE. Okay. 60,000 by AE into dx. So it comes out to be 60,000 by, you take this 4 to numerator, 240,000 by pi into 120 plus 0.2x 40 plus 0.2x into 2.1 into 10 power 5. E is constant here. Now, by integrating this between the limits 0 to n, this is sigma x by e into dx, ex into dx. Okay. So now integrate this between the limits 0 to n. By integrating, we will get delta L2, change in length of, by integrating this and substituting the values, you will get delta L2 as 0.005705 n. So total change in length or total compression delta L is delta L1 plus delta L2. Delta L1 already we have calculated the extension of portion LM 0.00758. Okay, so delta L is delta L1 plus delta L2 0.005705, that is 0.01328 millimeters. So this is the total compression of the member with a cylindrical hole. Okay, so that's how we'll work out the problems on tapering bars. Yeah, that's all for this session. Let us discuss some more examples in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.